Okay, let's look at theorems and the terminology associated with theorems. Well, an axiom is a statement accepted without proof. So the angles in a straight line add up to 180. We just accept that axiom. A theorem, on the other hand, is a statement which can be shown to be true via axioms and some logical argument. A corollary, which we've met before, is a statement attached to a proven theorem that's already gone ahead of it, which follows obviously from that proven theorem. So we make statements based on the theorem that was proved before, because they seem to be obvious anyway. The converse of a theorem is the opposite or the reverse of the theorem, and the word implies, this is the symbol, one result logically follows from another. So if something is equal to something, then that should imply that basically the next thing equals something else. Okay. So let's look at some theorems now. Let's look at theorem 4, and it's to show that the angles in a triangle add to 180. So you're given a triangle ABC with angles marked 1, 2, and 3. So here it is here. Okay, and you're to prove that the sum of the three angles is equal to 180. So how do we prove that? Well, the first thing is, in a construction, you draw a line L through the point A parallel to BC. Okay, and you mark the angles 4 and 5. Then, we'll start with the proof then. Angle 2 must be equal to angle 4, because if you think about it, they're alternate angles between two parallel lines, and this acts like a transversal. Okay, and that's the same for 3 and 5, alternate angles, transversal going through parallel lines as well. 4 and 1 plus 5, these three add up to 180, okay, straight angles. And so if that's the case, then we can just substitute in 4 and 5, substitute 2 and 3 in for those, because we've proved they're equal up here. So that means that 2 plus 1 plus 3 is equal to 180. And as we said at the end of a proof, QED, quod erat demonstrandum, and that means this from the ancient Greek, but it's in Latin, which had to be demonstrated. Okay, next theorem then. Theorem 6. Each exterior angle of a triangle is equal to the sum of the interior opposite angles. Okay, so you're given the triangle ABC with BC extended to point D out here. Angles marked 1, 2, 3, and 4 are also given. So you have to prove that this angle 4 is equal to this plus this, 1 plus 2. So here's the proof. So angle 3 and 4 is 180 degrees, because it's a straight line angle. And angle 1, 2, and 3 is equal to 180, because that's the sum of the angles in a triangle. Therefore, angle 3 and angle 4 is equal to angle 1 plus 2 plus 3. So if you take 3 from each side, you get to see that angle 4 equals angle 1 plus angle 2. Theorem 9, in a parallelogram, opposite sides are equal and opposite angles are equal. Okay, so here's our parallelogram ABCD, and we're to prove that AB is equal to DC and AD is equal to BC. So the construction is to draw a diagonal BD and mark the angles 1, 2, 3, 4. And the proof says that in the triangles ABD and BCD angle 1 is equal to angle 3, because they're alternate, because AB is parallel like that. So that the diagonal kind of acts like a transversal cutting through the two parallel lines. So 1 is alternate to 3, 2 is alternate to 4. Remember your old Z shape. And also DB is equal to DB, of course it is, because they're common sides. So really, the triangles ABD and BCD are congruent. They're the very same, due to the fact that they have a side that's caught between the two angles that are the same. So with angle side angle in one triangle and angle side angle in the other triangle. Angle side angle, angle side angle. Okay, so therefore when they're congruent, AB must be equal to DC, the sides opposite the corresponding sides opposite the equilateral equal angles, and AD is equal to BC, corresponding sides. Okay, so the angle DAB is equal to DCB, again corresponding angles in congruent triangles, and the angle ABC is the angle ADC. Okay, because angle 2 plus 3 is equal to 1 plus 4. So that must mean that the opposite sides and opposite angles of the parallelogram are equal. Okay, theorem 14. In a right-angled triangle, this is Pythagoras, the square of the hypotenuse is equal to the sum of the squares on the other two sides. So we're given a triangle ABC in which A is a right angle, okay, and we're proving that BC squared is equal to AB squared plus AC squared. So the construction is to draw a line AD perpendicular to BC and mark the angles 1, 2, 3, 4. And the proof goes like this. Consider the triangles ABC, ABC, the bigger triangle, and a smaller triangle ABD. Okay, so I kind of have them done here. If you look at those two triangles, angle 1 is common to both. Angle BAC is equal to angle ADB, 90 degrees. Therefore, ABC and ABD are similar. Okay, note we're not saying they're congruent, we're saying that they're similar. Okay, and if that's the case, then we can use our ratio of the corresponding sides, and we can say that BC over AB is equal to AB over BD, or cross multiplying AB squared equals BC by BD. We'll call that A. Then if we consider the triangles ABC and ADC, then we can say that the angle 2 is common to both. Angle BAC and angle ADC is 90 degrees. Therefore, triangles ABC and ADC are similar. So using our ratios again, we can show that AC squared is equal to BC times DC, and we'll call that B. And if we add the two terms now, we'll see that AB squared plus AC squared is equal to this plus this. Okay, and so we'll leave that as it is. We'll take BC, the common factor, out of both of those. That's the same as BC times BD plus DC. But BC is equal to BD plus DC, so that's the same as BC. So AB squared plus AC squared is equal to BC squared. So basically BC squared is equal to AB squared plus AC squared. Now, theorem 19. The angle at the centre of a circle standing on a given arc is twice the angle at any point of the circle standing on the same arc. So we're given a circle K with centre O. A, B, C are 3 points on K. The angle AOB is at the centre. The angle ACB is at the circumference. Both stand on the arc AB. Okay, so to prove angle AOB is twice angle ACB. Okay, so to solve this, construction we use is that we join C to O and extend through D. So we just draw a line from C to O and extend through D. And the proof is that angle 3 is equal to angle 5, as the triangle AOC is an isosceles triangle. So that's very important, comes up often. And angle 1 is equal to angle 3 plus 5, because they are equal to, where the exterior angle is equal to the sum of the interior opposite angles. So therefore, angle 1 is equal to 2 times angle 3. And similarly, angle 2 is equal to 2 times angle 4. So if we add these up, if we have angle 1 plus angle 2 is equal to 2 times angle 3 plus 2 times angle 4. Angle 1 plus angle 2 is equal to 2 times angle 3, angle 4. So that's the very same as saying that the angle AOB is equal to 2 times the angle ACB.